Hi everyone, welcome to the final part of this week's session in which we will be looking at effect sizes in a bit more detail. So to get us going, I'm going to revisit one of the analyses that I talked about in the Between Participants ANOVA lecture. So these are the output from a two-way analysis of variance, a 2x2 analysis of variance where we have two independent variables, status and audience, and the interaction between them. And I walked you through some of the crucial features of that output, highlighting, for example, the significant main effect of status and the not quite significant interaction between status and audience. And I suggested that that interaction could be written up in API format as follows. So I directly addressed, I guess, most of the components of this little bit of write-up here. But I didn't really focus in so far on this last bit, this last value, the 0.06, which is a partial eta squared. This value here under the partial eta squared column. And we got that bit of output by making sure that this particular option under effect sizes in Jamovi was checked. And we can also ask for other options such as eta squared, in addition to partial eta squared, as well as some of the others as well, omega squared and epsilon squared. So that's where it came from, but what is it and why do we need it? Well, partial eta squared is a measure of effect size. Okay, so how are effect sizes different from p-values? P-values are often, I guess, intuitively as one of the first places we look for our output in terms of interpreting the findings. Well, let's think first of all about what a p-value actually tells us. It indicates the probability that the data we have observed, or more specifically, the data that we have observed or more extreme, would have come up if the effect didn't really exist. In other words, if the null hypothesis was true. In contrast, an effect size tells us something more about the magnitude, the size of the effect. And that can therefore be used to say something about its importance in a more practical sense. Here you can differentiate between significance in the statistical sense and importance or significance in a practical sense, particularly when it comes to explaining variation in a dependent variable that we're interested in. So why are effect sizes important? Well, one of the key things to remember about p-values is that for a given difference, let's say the difference between two means, the p-value for that same raw difference will change as a function of sample size. That has a number of implications, one of which is that, for example, very small and potentially trivial effects can be significant if we have a very large sample. So we're still left with the job of interpreting whether those significant effects are actually practically meaningful. In contrast, measures of effect size are unaffected by sample size. Now that has a number of very useful properties. Firstly, it allows us to compare an effect across several different studies that may themselves vary in terms of sample size and in terms of significance values. Effect sizes also provide a basis for the synthesis of quantitative findings in a meta-analysis. The effect size is the key unit that you extract from many different studies if you're combining them in a meta-analysis. And effect sizes are also a crucial component of power calculations, of power analysis, that help us to estimate, for example, the sample size that we might need to detect an effect of a given size with a given level of power. So these properties of effect sizes have led many eminent figures to suggest that actually it's effect sizes rather than p-values that are the most important bit of output that you get from your analysis. So for example, Gene Glass says here, Gene Glass is the originator of meta-analysis. He suggests that actually statistical significance, your p-value, is the least interesting thing about the results. You should instead describe results mainly in terms of measures of magnitude. You should be discussing not just does a treatment affect people, but how much does it affect them. Likewise, Jacob Cohen, who is the most cited sort of statistician, researcher in relation to effect sizes and power, according to him, the primary product of research inquiry is one or more measures of effect size, not p-values. And likewise, the APA Task Force on Statistical Inference emphasizes that no matter what you're doing, always present effect sizes for primary outcomes of statistical analyses. So effect sizes are important. In practical terms, though, it can be tricky because there are many, many different measures of effect size out there in circulation. So I'm going to run you through three main types of effect size that you might see. The first one I'm calling estimates of the amount of variance accounted for in an outcome variable by an effect. Okay, so an effect size of this type can broadly be understood as a proportion, or if you multiply it by 100, as a percentage. So an effect size of 0.03 indicates that 3% of the variance in an outcome variable can be accounted for by the effect of the variable that you're looking at. Or likewise, if the effect size is 0.37, 37% of the variance in the outcome variable is attributable to the variable that you're looking at. Now, there are many, many different types of sort of approximations for the amount of variance accounted for in an outcome variable. Some of the most common ones that you will probably have come across already and may well see as you develop, is one is an R-squared, which is often used in conjunction with correlation, with regression, and also potentially with analysis of variance, as we'll see. The two actually that are most commonly associated with analysis of variance are eta squared and or partial eta squared. Alternatives for ANOVA also include omega squared and a Cohen's F squared. Okay. Those are all sort of variations on the same principle that we're finding or using a metric of how much variance in the outcome variable is accounted for. But they're also not entirely interchangeable, as we'll come to in a bit. The second main sort of type or family of effect size measures are what you might call standardized effect sizes. And by standardized, I mean they think about effects in terms of standard deviations. Okay. One quite common set or type is the standardized difference between two means. So for example, a Cohen's D or Hedges G. You'll see those used most commonly in conjunction with t-tests. Now, in terms of what a value means, a Cohen's D of 1 means that the means of two groups differ by one standard deviation. If the D is 0.7, it means those means differ by 0.7 standard deviations. There are actually several different types of Cohen's D or ways of calculating Cohen's D, depending on whether your design or the comparison of the two means involves independent groups or non-independent groups. I won't go into that in any more detail here, but you can find a link to a very useful spreadsheet in the link from the slides. Another form of standardized or standard deviation based effect size measure is the standardized regression coefficient, or the beta coefficient, that you'll see used with in relation to individual parameters or individual predictors in regression. Now, that's something that we will be revisiting in a bit more detail in the regression session. The third type of effect size measure is a type that we won't really encounter again in the context of this module. And they are effect size measures that are used in relation to categorical outcome variables. Now remember that all of the techniques that I'll be covering in this module relate to outcome variables that are continuous. Okay. If you're analyzing data that has a categorical outcome variable, the most commonly used effect size might be an odds ratio, for instance. Now, an odds ratio indicates the likelihood of that an outcome will be in one category rather than another as a function of a unit increase in a predictor. So, for example, if you're looking at the effect of alcohol consumption on whether or not someone is subsequently diagnosed with liver disease, okay, if the odds ratio in that analysis is 2.3, it means that for each additional unit of alcohol, that will increase the odds of contracting or having liver disease versus not having liver disease by 2.3 times. Okay, so as an example of a technique in which you might see an odds ratio used as an effect size, that would typically be with something like logistic regression, which is basically regression but with a categorical outcome variable rather than a continuous outcome variable. So what are the reasons for running you through the different types of effect size measure that you might encounter is to make this really important point. Effect size measures can vary, and vary a lot, in terms of the range and meaning of possible values. So for example, most of those variance accounted for measures, that first sort of family of effect size measures I mentioned, such as R squared, they can't be greater than 1. 1 is their maximum value, indicating that 100% of the variance in an outcome is associated with the variable that you're using as a predictor. In contrast though, standardized difference measures, measures that look at effects in terms of standard deviations, such as Cohen's d, they can in practical terms go up to even 3, or in theory go even higher. Actually, it can range in theory up to infinity. Even within that family of variance accounted for effect size measures, they aren't also strictly equivalent. So for example, a Cohen's f squared is not directly equivalent to an eta squared and needs to be converted using a formula. So the moral of this story is that a given value, a given number for an effect size, therefore has really, really different meanings depending on what size of effect it is. So for example, as we will see in a little bit, an effect size of 0.2. Well, what effect size are we talking about here? If that was a Cohen's d, that is just in the upper end of a small effect in Cohen's terms. But if we're talking about an eta squared, that's actually a very large effect. Okay, so the meaning of a value, if you hear something like the effect size was x, 0.2 or whatever it is, the first thing you should wonder is, well, what type of effect size measure is that? Okay, because that will help you make sense of what the value means. Okay, now in terms of getting from one type of effect size measure to another, converting one to another, I've included links to a couple of very useful conversion calculators which are accessible via the slides. So I've already touched upon that issue of how to describe or characterize the magnitude of a given size of effect. How big is a big effect, or a small effect, or a medium effect? Well, this is actually quite a sort of a controversial topic, and I guess one of the common themes in research that makes reference to small, medium, or large effects or whatever, tries to sort of characterize the magnitude of the effect, they will often refer to a set of guidelines produced by Cohen. So for each of these effect size measures, so a Cohen's d, an r, or an eta squared in between participants ANOVA, he suggested that we can use rough cutoff points for small, medium, and large effects. So for Cohen's d, a small effect is something like 0.2 or less. In between 0.2 and 0.5 is medium. 0.5 to 0.8 is large, and above 0.8 then your effect is large or larger. Okay. Similarly, an R of 0.1, 0.3 and 0.5 correspond to those cutoffs for Cohen, and an eta squared 0.01, 0.06 and 0.14 respectively correspond to small, medium and large effect cutoffs. A little bit later, Bakeman developed a similar set of guidelines or suggested cutoff points for small, medium and large effects for a measure of generalized eta squared used in relation to repeated measures ANOVA. Okay, so those are generally a little bit larger than the between participants eta squared that you might see, partly because the way in which it's calculated, the denominator, because it's a repeated measures design, means that the effect sizes tend to be a lot larger. Now, the most important thing here is these are, as Cohen himself quite strongly emphasized, these are arbitrary. There's nothing inherent in these values that make them small, medium, or large. They are just a judgment based on what is actually useful or typical within a particular field of research. So particular fields of research may see smaller effects much more commonly. Others might see larger effects much more commonly. Okay? So conventions as to what is a small, medium or large effect will vary as a function of the research area and in turn actually as a function of the research method that you use. So while it is really common to refer to or see reference made to cutoffs for small, medium and large effects, they are ultimately arbitrary. They have little absolute basis. Okay, so a judgment about the meaningfulness or size of a given effect size value, yeah, that's something to make a more considered judgment on than simply using these arbitrary cutoff points. So I'm going to close off by looking in a little bit more detail at effect size in analysis of variance. So this is the output table, again, that I showed you earlier. So let's look first at eta squared and how it's actually calculated from the values that we have in this table. Okay, so I'm not talking here yet about partial eta squared, but rather about eta squared, which is this column here. And eta squared for each of these effects is simply the proportion of the total variance, okay, accounted for by a given effect. Okay, in other words, it's the sums of squares of the effect divided by the total sums of squares. So, for instance, the effect size, the eta squared for in-group status, is the sums of squares of the effect divided by the total sums of squares. 8.42 in this case divided by 131.55. And that gives you 0.06. Now, the problem with eta squared, and the reason that people often report or prefer partial eta squared, is that eta squared tends to decrease as further variables or effects are added to the model, even though the effect itself stays the same, as it were. So partial eta squared is suggested as a solution to that because it provides an estimate of the size of the effect while partialing out variance explained by other effects in the model. Now, proponents of that effect size measure suggest that that allows easier comparison of effect sizes or variables across studies that have different designs, that for example have different factors or different covariates alongside the predictor that you're interested in. So the calculation or the formula for a partial eta squared is a little bit different. Again, though, it's the sum of squares for the effect that you're interested in divided by, and this is a little bit different, the sums of squares of that effect plus the error or leftover variance, the error sums of squares. So let's see that in practice. Okay, here's our output table. The partial eta squared is the sums of squares of the effect, 8.42, divided by the sums of squares of the effect, 8.42, plus the error, in this case in Jamovi language, the residual sums of squares. Okay, so we calculate that and we get 0.07. So that's where the partial eta squared comes from. Okay, it's simply this divided by this plus this. So last thing to say is in relation to two caveats regarding effect size. And I'm saying here effect size in relation to ANOVA, but also I guess effect size more generally. The first is that partial eta squared is recognized to be a biased measure in the sense that it overestimates the effect size in the population as a whole. Because technically partial eta squared and eta squared technically estimate the size of the effect in the sample rather than the population as a whole. And it actually typically overestimates the effect in the population. In other words, the actual population level effect for a given method tends to be smaller than the partial eta squared found for a particular sample. So for that reason, you will see people often advocating for alternative measures of effect size, such as omega squared or epsilon squared. I won't go into that any further. If you do want to delve into it a little bit more yourself, I've included a link to some further discussion. The second thing to say about effect sizes, not just in relation to ANOVA, but effect sizes in general, is that while I said they don't vary as a function of sample size, they do vary. They vary a lot depending on methodological features of your study. They are fundamentally a product of a method. Okay, so what that means is the size of an effect between two variables depends very, very much on how those variables are operationalized. Okay, for instance, an effect size in an experiment will be much greater if you have a stronger manipulation of your independent variable. Let's say, for example, we have a study looking at mood on some sort of outcome variable like helping behavior. Okay, let's say the manipulation of mood is via a mood induction, where you have a control condition versus a condition in which people are induced to have a positive mood. Okay, now you can do that in quite gentle or subtle ways, such as asking them to maybe they're being paid a compliment or something like that, or they're being asked to remember a happy memory. Okay. Alternatively, you could manipulate that in a much stronger way. You could, for example, tell participants that you were just, apropos of nothing, going to give them £1,000 or £5,000 each, assuming you had unlimited resources. Okay. Now that presumably, I guess for most people, that is going to be a very positive, happy event, being given lots of free money. Okay. So in that case, we might have a much stronger manipulation of mood. All right. And in that case, the observed effect size of mood will likely be much bigger because the manipulation itself is much stronger. Likewise, on the dependent variable side, you're more likely to get larger effect sizes when you have sensitive and relevant outcome measures. So that might mean, for example, an outcome measure that is not noisy, that's a very good and precise measure of the thing that you're interested in. And by sensitive, I also mean features of the design that increase the sensitivity of your measure to picking up effects of a manipulation. That might be, for example, something as simple as having your measure immediately after the manipulation, as opposed to, say, 6 months later. So in that hypothetical study, looking at mood on, let's say, helping behavior or willingness to help other people, if our measure of willingness to help other people is carried out 6 months after the mood induction, it's much less likely to pick up an effect than if you have measured it immediately after the mood induction. Okay. Now what that means in effect size terms is that the effect size will be bigger when that measure is immediately after the manipulation compared to 6 months later. Okay. So all of this is to say that effect sizes don't represent some abstract relationship between variables. They are fundamentally the product of a method that is applied to look at the relationship between two variables. And as you change features of that method to make them stronger or weaker, you will see changes in the effect size as a result. Okay, so just a key thing to remember. Okay, that's it for this session. Next time round, we will be looking at analysis options for repeated measures designs. Okay, focusing on mixed models. All right, thanks very much. I'll see you then.